As we start a new chapter here, we're going to take a look at some important shapes that we can represent mathematically, algebraically. And among those shapes, one of the important shapes, the first one we're going to look at here is an ellipse. So this is an ellipse. It's kind of a stretched circle. And there are a couple things. We're going to talk about the formula here in just a second. But the key idea here is that you have these 2 points called foci, I guess. Don't know how to do the plural. Foci. And what makes an ellipse special is that any point on the outside of the ellipse is the same distance from these two foci. So it doesn't matter where I were to go. But if I added up the distance between those two foci, I cannot say that, foci, then they would be the same length. The length of these lines would add up to be the same, no matter where you are on the outside of the ellipse. So that's what makes an ellipse special, is its relationship to these foci. Now, we're going to take a look at the formula in just a second, but let's look at the formula first, and then I'll come back to this. So here is our formula. Now, what we're going to notice here is that a, on the bottom here under the x squared, the distance a is going to be that distance from your center to the outside of the ellipse. But we have two different axes. Because it's like a circle that's been pulled, we have what's called a major axis. That's going to have the foci on it, and it's going to be the longer one. Or we have a minor axis, which is obviously then going to be the shorter one. Now, it doesn't have to get pulled horizontally. It could get pulled vertically. So it's possible. So there's actually a second version of this equation. So it's possible that the longer side is along the y, is vertical. So it can be either. So you take a look here at your equation. You say, okay, is my longer side under the x or under the y? And that'll let you know how we're going to stretch this. Okay, so that value of a, I go back to the picture, that value of a, that's the distance from here to the outside of the ellipse. So if that distance is a, and this distance is a, then the length of this major axis is 2a. So then we also had the b here. The other one is going to be the length of the minor axis. So if we look at that, this is b. And so obviously the length of the entire minor axis is 2b. Let's see, anything else I need to tell you about here? Okay, yeah, the last thing that's super important is we need to be able to find the distance to those foci. And here's where it's derived from. I've scribbled too much on this, but if we were to make a right triangle here, so we've got this formula, c squared equals a squared minus b squared. Now it sounds a little different because we're used to a squared plus b squared equals c squared. It hasn't changed anything. It's based on the Pythagorean theorem, but what we're looking at here is that this length is c, and so what we're doing to work this, to create this equation, is we're creating this right triangle. This entire length here then, we don't know c, so we're going to use a minus c. So this whole length is a. Take away the c, and that's how we're going to be working with this triangle here. So again, it's just a derivation of the Pythagorean theorem. It's just based on the fact that we're running a right triangle to the foci. Okay, so let's get into it here. Those are all the pieces that we're going to need to solve one of these. So they want us to create the equation. Well, we only have the vertices and the foci, so let's take a look. If I know, first thing that strikes me here is I have these vertices and this foci. Well, look, they're on the same line. Do you see that they're on the same axis here? So this is the major axis. So the plus or minus 8 has to be my value of a. So a is 8. And now the formula requires you to square it, so a squared is going to be 64 right here. Now, we know the distance to the foci is 5. So what we're going to need to do is that formula c squared equals a squared minus b squared. Because we have a and we have c, but we don't have b. So we plug that in here, we get 25 equals 64 minus b squared. We solve this, b squared is 39. And so, well, b would obviously be the square root of 39. But we want b squared for the formula, so now we have this. And where is it? Yeah, we've got everything we need. So we knew A, we knew C, and then we used that information to find B, plugged everything into our formula. Okay, so let's try again here. So do you see here, this time, what I can tell is that the major axis is running through the y. So A is going to be underneath the y this time. We square that, A squared is going to be 16. So C is equal to the square root of 15, so C squared is obviously 15. So I've got 15 equals 16 minus B squared, just using that C squared equals A squared minus B squared equation. Okay, so let's solve this. So I'm going to send B squared to the other side. I'm just doing some algebra. I'm going to send the 15 over here. B is going to be 1. So B squared is going to be 1. So I hope I didn't go too quickly here. I'm moving the 15 over, I get 1. Moving the B squared over, square root both sides, B is 1. And there we go. Okay, now obviously the center isn't always right at 0, 0. Just as if you recall how we did this with the parabola back when we were doing the standard form of that some time ago, earlier in college algebra, we can shift it, and the vertex was at the point HK. Well, we're going to do exactly the same idea here with the ellipse. We can shift it, and just like with the parabola, the formula is built with a minus. So I've got x minus h, y minus k. That's my shift. So this is the center, HK. Okay, everything else is the same. We're just going to, if we're going to take that A, we're going to adjust it along the major axis from the center. And so we're going to go right and left, up and down based off that new center. That's it. Everything else stays the same. So obviously we could have two versions of this. This version would be where the major axis is going vertically. Okay, everything is the same there. We're just adjusting from the fact that we're at this new center HK. All right, let's try it here. So this is the formula that we're trying to come up with here. If we notice, okay, so they give us these vertices and the foci. This is on the y-axis. The change here is happening, the foci, all of this is on the y-axis. So we know that A is going to be under the y. All right, so let's find HK. We can actually find everything we need just from right here. So what we want is the middle of these vertices. And so we've got, we're just finding the midpoint of these right here. So if you find the middle of this, if you add -2 and -2, you get divided by 2, you get where you were. So I can just see this visually. If you look at this, the value of x isn't changing. So that's the value I'm going to have for the h. If you look at this, -8 and 2, that is a distance of 10. If you cut that in half, they're not right about this. Hold on, let me think this through. I think they're off. No, they're not off, I'm off. I was trying to find the distance for A, but so if we're finding the center, we do just want to average these. So there's a distance here. We're going between -8 and 2. So we add those together. The middle of that, so what I was doing is this distance is 10. Cut that in half is 2. So what I was finding is that A is going to be 5. So I'll talk you through that in just a second. But so if we're finding the middle, if we're looking for the center of this line, we just add the 2. We're going to get -6 divided by 2, -2, -3. So I said this really poorly. Here's all we're doing. If I know these are the endpoints of that major axis, let's average them. If we average them, that would be the center, which is what we're doing right here. Okay, now let's find A. So here's, this is what they're doing. The distance between -8 and 2 is 10 spots, isn't it? Between -8 and 2 is 10 spots. So that's the distance. So if you cut that in half, so the major axis is 10. If you cut that in half, you get 5, which is how they came up with A is 5. All right, so now we know A squared, and it's going to go underneath the y, so we've got this value right here. Now we need B squared, but the only thing we have to work with is the foci. So let's find the distance for c. So from here to here, we have 8. So the thing is symmetrical. So if that's 8, we cut it in half. So the distance from one foci to another, the distance there is 8. Well, the length of C is just from the middle to that point, so C must be 4. Okay, so we've got C squared and we have A squared, so we can find B squared. Just solving this, swinging the negative B squared to the other side, send the 16 over, B squared is then 9. Okay, so we have everything we need. Just remember, we were stretching this ellipse. It was the longer side, the major axis was vertically, so the 25 is under the y. Also don't forget that when we build the formula, the h and k go in, but the h and the k, the formula is built with a negative. Okay, let's try this once again if you want to give it a shot. Now, when I'm looking at these here, what I see is that all the action this time is happening on the x. So it's going to be x squared over a squared. Now, we've shifted as well. I shouldn't have done that. So, hold on. Okay. All right, so what is the length here? Or first of all, let's find the center. We can do this either order. Let's find the center here. So I'm going to add these 2 points up. Get negative 3 plus 5 divided by 2. 3 plus 3, obviously, divided by 2 is going to give me right back to 3. So my center here is going to be at 2. It's going to be 1/3. So this is my value of h. H is 1, and k is going to be 3. So we could drop those in, but let's go ahead and we need to find a and b here. So the distance here, the major axis is along the x, and the distance from negative 3 to 5, that is a distance of 8. So technically the way you could do this is you do the last minus the first. So 5 minus negative 3, that gets me a distance of 8. I'm just doing that in my head, but that's what you would do, the last minus the first. So you get this 8, that's the distance of the major axis, but if we cut that in half, a is 4, because that's what a is, the distance from the center to either one of the sides. Okay, so we've got a is 4, so a squared is 16. All right, we've got everything we need to create the formula except b squared, but we can find that because we know c. So if this is centered at 1, do you see what's happening? We have 1 minus 2 square root of 3 and 1 plus 2 square root of 3. So we are just going to, hold on, let me do it like I did before in case you're confused. Okay. I'm just going to do the last point minus the first point to find the distance here. So make sure you understand that negative would distribute here, and what I'm going to get is, can you see this? The ones will cancel, and now I have a positive, a second 2y. Let me just show it. So the ones will cancel. Now I've got 4. Remember how this works? Radical 3 is like a variable, so this is 4 radical 3. Okay, now that's the distance all the way across from one foci to the other, but we want half of that. So c is half of that value, so it's 2 radical 3. All right, so c is 2 radical 3, but we want c squared. So c squared would be 4 times 3. Do you remember how the squaring of this works? It'd be 4 times 3, we'd get 12. So if you're not sure about that, 2 radical 3 times another 2 radical 3. Multiply the outsides, multiply the roots together. That's where I'm getting the 4 times 3. Okay, so c squared is 12. So we're still not done. We're almost done. Sorry, we're running out of space here. So c squared equals a squared minus b squared. So I'm going to switch that to the other side. B squared is 4, b is 2. Okay, so let's put our formula together. Now remember, it's built with a negative, so x minus h, which was 1, over, which our major axis is on the x, so we want a here. and then y minus 3 squared, and we want b here, which is b squared here, which is 4. And there we go. Okay, I hope that makes some sense, getting introduced to the ellipse. Special property is that from those two foci, the distance to any point on the ellipse is always the same. We've got to check to see where the major axis is. A squared is always going to be under the major axis, whether that's the horizontal, the x's, or the verticals, the y's.